This is a reminder to you of what we're doing. We just covered molecular shapes, and now we're going to cover electronegativity and bond polarity along with molecular polarity. These two really belong together. So let's look at electronegativity and bond polarity. The goals are to understand electronegativity and use it to determine the polarity of bonds, and then use electronegativity and formal charge to predict the charge distribution in molecules and polyatomic ions. So let's look at electronegativity and bond polarity. So you have two types of covalent bonds based on electron distribution. You've got the nonpolar covalent bond, where the electrons are shared equally, and this is going to happen between two atoms of the same element. So if you have two hydrogens, they share these electrons equally. If you have two carbons and you have a double bond, they share these electrons equally. So if they were to split, you'd expect each one to take half. And here, if you have two nitrogens, you would expect these to share the electrons equally. Now, there are also polar covalent bonds, and there are different degrees of polarity. You can have kind of polar covalent bonds and very polar covalent bonds. So what is a polar covalent bond? It's where the electrons are shared unequally. And it results in one atom being slightly negative. So we use this symbol here that's called a delta negative. That's the more electronegative atom, the one that attracts electrons to it better. And you have the other one, the other atom is going to be slightly positive, which we use a delta plus, and that's going to be the atom that's less electronegative. So in this example above, hydrogen is the less electronegative atom and chlorine is the more electronegative one. So if you look at these electrons here and you look at how they're distributed, instead of being evenly distributed like we have here with a nice even ellipsoid, it would be more like that, where the electrons are closer to the chlorine than they are to the hydrogen. So this is a polar covalent bond. So how do we determine if a bond is going to be polar covalent? Well, the answer is, if they're not the same atom, it's a polar covalent bond. But to what degree? So let's take a look at how we actually assign these. We look at something called electronegativity. So electronegativity is a measure of how well an atom attracts shared electrons. So this sounds a lot like electron affinity, but it's not, because we're not attracting electrons just from outer space, if you will. We're attracting electrons that we already own. So how well we are winning the tug of war for the electrons with that other atom. The electronegativity scale is a scale of 0 to 4, less to more attraction. So 0 is less attraction, 4 is more attraction. It's an arbitrary scale. It's often used to distinguish between covalent bonds and ionic bonds. So if the difference between electronegativities is really big, we say it's an ionic bond. And if the difference is really small, we say it's a covalent bond. Fluorine is the most electronegative atom at 4.0. And if you look at a period, when you go across from left to right, the electronegativity increases. And when you look at a group, when you go from bottom to top, the electronegativity increases. So if we put a few atoms in here, fluorine, oxygen, and chlorine, fluorine is more electronegative than chlorine, and fluorine is more electronegative than oxygen. It's hard to compare elements if they're not in the same group or not in the same period, although it can be done at times. Now, before we move on, I do want to say that there are some electronegativities that you might want to just become aware of. Fluorine, it's a 4O. Oxygen's a 3,5. Nitrogen's a 3O. So based on this, what do you think carbon is? Okay, you guessed it, 2,5. And boron would be 2O. Beryllium would be 1,5, and lithium would be 1,0. So period 2 is pretty easy to understand. You just start at fluorine with a 4O and you drop by half each time. Now our book says beryllium is a 1.6, but we're not going to haggle. 1.5 is close enough. Another one you might want to know is hydrogen, which according to our book is a 2,2. So hydrogen is more electronegative than boron, but less electronegative than carbon, but pretty close to carbon and pretty close to boron. Okay, so these are some electronegativities you might want to know. Okay, so what we're going to do now is we're going to estimate bond polarities. We're going to, for each of these bonds, try and figure out which is the more electronegative atom, if there is one, and which is the less electronegative. So here for boron and fluorine, we know already fluorine's the clear winner. So we're going to put a slightly negative there because it is the most electronegative atom, and a slightly positive here on boron. Now, what about boron and chlorine? Well, we might want to look those up. If we take a look at the slide that we just looked at and look at that scale, you can see that boron's a 2O. So boron's a 2O. I happen to know that chlorine is really close to a 3O. So which one's more electronegative? Chlorine. So it's going to be the slightly negative side, and boron will be the slightly positive side. So these are both polar covalent bonds. And we've indicated which side is more negative with a delta negative, and which side is more positive with a delta positive. Okay, let's take a look at these next two here. SiO. So this one, they're not in the same group and they're not in the same period. So how are we going to do these two? Well, let me show you how to do it. I'm going to fold this paper over. And here is silicon on the periodic table. Carbon is above it. Nitrogen is next to it, and then oxygen. Now, when we look at electronegativities, we know for darn sure carbon is less than nitrogen is less than oxygen because it increases going to the right. Now, what about silicon and carbon? Well, we know that when we go up, it gets bigger. So that means silicon has to be smaller than carbon. So voila, we now know what's more electronegative, silicon or oxygen. Oxygen is. So for silicon and oxygen, we're going to put the slightly negative on oxygen because it's more electronegative, and the slightly positive on silicon. And we can do this even though we don't know the values. Okay, what about phosphorus and phosphorus? Well, we don't know the electronegativity of each, but it's exactly the same. So here, this is a non-polar covalent bond. And here, this is a polar covalent bond. And that's how you use bond polarities to determine whether or not this is how you use electronegativities to determine whether or not a covalent bond is going to be polar. Now, we don't have any examples here with a double bond, but this works for double bonds. So if we looked at a carbon-nitrogen double bond, here, the nitrogen would be slightly negative and the carbon would be slightly positive. Or if we looked at a carbon-oxygen double bond, the oxygen is more electronegative and the carbon is slightly positive. Now, these are both polar covalent. But the carbon-oxygen is more covalent or more polar. Why do we say it's more polar? And the answer is, well, because oxygen is more electronegative than nitrogen. So the difference between electronegativities is bigger between carbon and oxygen compared to carbon and nitrogen. These are neighbors, these are not. Okay, I want to remind you that we looked at something called atom formal charges in covalent molecules and ions. So this is something we've already covered. using formal charges. The best structures have all atoms with a formal charge equal to 0. And if you have a positive formal charge, it should be on an atom with a smaller electron affinity and a smaller ionization energy. If you have a negative formal charge, it should be on atoms with greater electron affinity and greater ionization. This is called collectively the electroneutrality principle. And the idea behind this principle is if you have a formal charge of 0 on each atom, that means you've got the electrons distributed pretty darn well. And if you are going to have a negative charge on something, you want it to have it on an atom that it turns out likes electrons better. Okay, now let's go back to this. We looked at these 3 structures. These are resonance structures for the cyanate ion. And here, how do we use the formal charges? Again, we want as many formal charges as 0 as possible because it means the electrons are distributed evenly. Here, the electrons aren't distributed evenly, so this is the worst out of the 3 resonance structures. And most people would say this is so bad that we don't even consider it as a resonance structure. Essentially, if your formal charges aren't 1s, you don't like them. Here we've got a 2. You really don't like that. So really it comes down to these 2 resonance structures. And which one is the better one? Well, because oxygen is more electronegative and has a higher electron affinity, it's going to have the -1 charge. And this is more likely. Now, if these are even 50-50, what would be the bond order here? Do you remember the bond order? Or it'd be not a double bond, not a single bond, but somewhere in between, right? 1 + 2 is 3, spread over 2 structures, it'd be like 1.5 bond. Now, since it's more like this one, it's going to be more like a 1 than a 1.5. It'll be like maybe a 1.25 or something like that. Okay. Now, let's take a look at a problem from our book about calculating and using formal charges. So let me scoot this over a little bit so we can read everything. So boron-containing compounds often have a boron atom with only 3 bonds and no lone pairs. So it doesn't have an octet. It's one of those ones that can get along without a full octet. Why not form a double bond with a terminal atom to complete the boron octet? To answer this, consider possible resonance structures of BF3 and calculate the formal charges of boron and fluorine atoms. So BF3, boron has 3 valence electrons. Fluorine has 7, so 3 times 7 equals 21 plus 3 for 24 electrons. So if we just look at the Lewis structure, we put boron in the middle because it likes to make 3 bonds, and fluorine likes to make 1. We put electrons around each fluorine, and we have octets on each fluorine, and here we go. So this is what we normally draw for BF3. This says, why not form a double bond? So let's form a double bond to this top fluorine here. So what I'm going to do is I'm going to take these 2 electrons on the top and make them another bond to boron. So now we have a double bond to boron. So you see each fluorine still has 8 electrons, but the boron also now has 8, whereas over here it only has 6. So they're asking us to take a look at these and use formal charges to tell us why this one is better than this one. Okay, let's go a step further and let's draw these in 3 dimensions. So how many pair are on the boron? 1, 2, 3. So what's the orientation of 3 pair? It's going to be trigonal planar. So we plug in the rest of the pieces. And this is what boron trifluoride looks like if we assume that there are only single bonds between the boron and the fluorine. What happens up here when you have a double bond? How many pair do we have now? We have 1, 2, 3. We still have 3 pair. So what's the orientation of 3 pair going to be? Trigonoplanar. So they both look the same. They're both trigonoplanar. So one of these is not better than the other. We can also look at what is going to be the molecular polarity. Well, what is the most electronegative atom here? Well, it's fluorine. Is the fluorine on one side of the molecule? Well, here we could say the 2 fluorines are on this side, or we could say the 2 fluorines on this side, or the 2 fluorines on this side. The fluorines are not on one side of the molecule. So these are both nonpolar. So let's take a look and let's find out the formal charges on each of these types of atoms. So we basically have 3 types of atoms here. We have the fluorine with 3 lone pairs and a single bond. We have the fluorine with 2 lone pairs and a double bond. And we have the boron with 3 bonds. And I'm going to move the sheet up just a little bit here. Well, I'll do this over here. We have a boron with a double bond and 2 singles. So let's get the formal charge of each of these. So the formal charge of this one is going to be based on this. So here, remember, formally we say that the atom owns all of the non-bonding electrons and it owns half of the bonding electrons. So here I'm keeping all the non-bonding electrons and keeping half. And we compare to the neutral atom. So the neutral atom has 7 valence electrons. They're exactly the same. So the formal charge on this guy is 0. Here, if we do the same thing, we say, okay, we own the non-bonding electrons, but we own half of these. There are 4 electrons there, so you only get half. And you compare to the neutral fluorine atom with 7 valence electrons. Look at that. That's only got 6, that has 7. What's going to happen to your charge when you lose an electron? Your charge becomes positive. So this guy is going to be a positive 1. What about a boron here? So the formal charge of this boron is going to be a boron with 3 valence electrons because we take half of each bond and we compare to the neutral boron atom, which has 3 valence electrons. So the formal charge here is 0. So if we go back up here and fill in formal charges, here you've got a 0, 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 here you've got a +1. Now, what about this boron here? Well, we could do it a number of ways. We could figure it out this way. So the formal charge of this boron is going to be a boron with 4 valence electrons compared to a boron with 3 valence electrons. And again, we're comparing it to a neutral boron atom with 3 valence electrons. So here, what happens to your charge if you have more valence electrons than you should have when you're neutral? You become negatively charged. Another way we could have assigned this is that if this is a 0, this is a 0, and that's a +1, all of these formal charges have to add up to 0 because this is a neutral molecule. So the only way that would work is if the boron formal charge was negative. So here, because they're all zeros, the electrons are evenly distributed. And remember, electrons repel one another. So we want to evenly distribute them around the molecule. Here, we have non-zero formal charges. So the electrons are not evenly distributed. And so this is not as stable as this over here. So why do we not make a double bond between boron and fluorine? Answer, you upset the distribution of electrons and you make something that's actually less stable. Okay, so let's put that off to the side. Now let's take a look at molecular polarity. The goal is to predict the polarity of molecules and understand why some molecules are polar, whereas others are non-polar. So, for molecular polarity, to actually measure it experimentally, what you do is you submit your sample to electric field, and if the molecules align, they are polar. That is, they have a dipole. And so when they align, the positive side will face one side of the electric field, the negative side will face the other side of the electric field, because on the electric field, you've got positive and negative. So this side would be the positive side of the electric field. This side would be the negative side because opposites attract. If you have a nonpolar molecule, they wouldn't align because they don't care. Okay, now if they do align, you say that they have a dipole. A dipole means that you got a slightly positive side and a slightly negative side. Now notice for the bond polarity, we used a slightly positive and slightly negative. Here we use this arrow with a positive sign on one side of it. That positive sign says that's the positive side. This other side means it's the negative side. And when we say positive side, we mean slightly positive. When we say negative, we mean slightly negative. It's not a full charge. So how do you assign molecular polarity? There's two ways to do it. So this is kind of the tougher way, but it's interesting. You define each bond as polar or nonpolar. Use these arrows for each bond, where the positive part of the arrow is on the slightly positive or less electronegative atom, and the pointy part of the arrows on the slightly negative side of the bond. And then you add the arrows as vectors. I'll show you what that means in just a minute. And when you add them as vectors, the added result is the molecular polarity, where this side is the slightly positive side, and this side is the slightly negative side. How in the world are you going to remember that this side of the arrow is the slightly positive side, other than that it looks like a positive? And the answer is, that's all you need. It looks like a positive, that's the slightly positive side. Okay, so let's see this applied. Now, let's take a look at carbon dioxide, and we know that the molecular geometry is this. So to do molecular polarity, you need to have the molecular geometry. So it's linear with 180 degrees. Now, since the oxygen is more electronegative, it's slightly negative compared to the carbon. So you see for this bond, I put the slightly negative on the oxygen, the slightly positive on the carbon. And for this bond, I did the same thing, the slightly negative on the oxygen, the slightly positive on the carbon. Now, for doing this, we want to change these positives and negatives into these arrows. So notice the slightly positive side is the positive side of the arrow, the slightly negative is the pointy part of the arrow. So I have two arrows, one for each bond. So when we add these arrows together, what we do is we say, start here, and I'm going to use this arrow first, 1, and this is where we go. So that's number 1. And then we add arrow 2 to this, and we get right back where we started. So when you get right back where you started, it's nonpolar. So that's adding them together. So that's a pretty disappointing example. Let's look at one where when you add them together, you get something out of it. So here's another molecule. This is a molecule called a formaldehyde. Now, in this molecule, this is trigonoplanar, and this is the molecular geometry, 120-degree bond angles. Now, when we look at these, since hydrogen is far to the left, it's going to be the least electronegative. Since oxygen is farthest to the right, it's going to be the most electronegative. So here's the electronegativities, En, in order from low to high. So here I'm going to draw arrows in for bond polarities. Since oxygen is more electronegative than carbon, I put the positive side of the arrow next to carbon, the pointy side next to oxygen. For the hydrogen-carbon bond, since carbon is more electronegative, and we can even say hydrogen is more electropositive, we put the positive part next to the hydrogen and the pointy part next to the carbon. And we do the same thing here. So we have these three arrows, which are vectors. Notice I numbered each vector, 1, 2, and 3. We're going to add them together now. So do you see this one arrow is right here? Do you see it's pointing in the same direction at the same angle? And then I put the 2 arrow in, and the number 2 arrow is right here. It goes straight up. And then I put the number 3 arrow, it goes up to the left at an angle. So when I add these 3 together, here's where I start and here's where I end. So there's my start and end. And you can see when I connect the dots where it starts and where it ends, I get an arrow going straight up. That's the molecular polarity of this molecule. And when we draw the molecular polarity on the molecule, we don't like to do this. So this is a no-no. You never see anyone do this. You don't put it in the middle of the molecule. You put it off to the side. So when you put it off to the side, this means that when we go straight across, this side of the molecule is kind of positive. Go straight across, this side is kind of negative. And that's how you add up the arrows as vectors. Here's another simpler example. This is a hydrogen cyanide. We know that hydrogen is less electronegative than carbon, which is less electronegative than nitrogen. So when we draw the arrows together, we're going to put a positive on hydrogen, negative on carbon, positive on carbon, negative on nitrogen. Now, when we add these 2 arrows up together, here's where you start, here's where you end. So you add them together and you get an arrow that's the sum of these 2 arrows. So this is the overall, molecular polarity of the molecule. And so here you can see I've drawn it down here. So what does this positive side of the arrow mean? This is slightly positive. What does the negative mean? Or the pointy part mean? This side is slightly negative, as we see here. So if I draw this molecule here as kind of a ellipsoid, and I just draw the ellipsoid without the atoms, what we see is a slightly positive and a slightly negative side. So why is this important? Well, it turns out that if you have another one of these and it interacts with another one just like it, this is how they will interact. Why do they orient themselves that way? And the answer is simple. Opposites attract. So the slightly positive of one molecule attracts the slightly negative of another molecule. Okay, that doesn't happen with nonpolar molecules. So it turns out that polar molecules kind of mix well, whereas nonpolar molecules don't really mix well with these polar molecules. These guys kind of exclude the nonpolar molecules. They have no attraction for them. Okay, now there's another way to assign molecular polarity. I've seen other people talk about it this way, but I just like it better. It's a lot simpler. So what you do is you look and see, and if you have a slightly negative side, it's going to be because it has the most electronegative element in it. And the slightly positive side is the opposite side. However, if the most electronegative element is in the middle, the molecule's nonpolar, or if the most electronegative element is evenly distributed, it's nonpolar. So let's look at those 3 examples we looked at before. Here's the one with carbon dioxide. Do you see the most electronegative atom is oxygen, but it's evenly distributed. There is no side with the most electronegative element. So nonpolar. And that's what we discovered before by adding vectors. Take a look at this molecule. What's the most electronegative? Oxygen. So that means the opposite side here with the hydrogens is kind of positive. So we draw an arrow going from the opposite side straight up to the most electronegative side. And here's your molecular polarity. And then lastly, we have this hydrogen cyanide. And notice, since nitrogen is the most electronegative and this is the opposite side, we draw an arrow going to nitrogen. Now, what if we had drawn these molecules differently? For instance, this guy right here. What if we had drawn it like this? What would you draw for the molecular polarity here? And the answer is this, in the opposite direction of this, because this molecule is upside down compared to this. So what does this arrow mean again? Does it mean that this molecule flies through space oxygen first? No. It means that the positive part of the arrow is the slightly positive side of the molecule, and the other side is slightly negative. Okay, so let's look at a couple of problems. Here we're going to look at sulfur tetrafluoride and nitrogen trifluoride to see if they're polar or nonpolar. And if polar, indicate the negative and positive sides of the molecule. So SF4 has 6 plus 4 times 7 electrons. 4 times 7 is 28. 28 plus 6 is 34 electrons. Okay, so we're going to have 34 electrons. I'm going to put my fluorines around here like this. Okay, so 4 times 8 is 32. We've used 32 electrons. So, how many are left over? 2. We put them on sulfur. So, how many pairs does this have? 1, 2, 3, 4, 5. So we're going to make a trigonal pyramidal, bipyramidal drawing. So it's going to look kind of like this. So that's your start of the trigonal bipyramidal. And where do we want to put the lone pair? On an equatorial placement. So we're going to put them right there. Now, this is one where the vector way of working does a better job than does it have a side that's mostly negative. So if we look at the vectors, can you see that you're going to have a vector that looks like this, a vector that looks like this, one vector that comes out towards you, and one vector that goes away from you, right? So when you add these all up together, can you see that these two cancel? And here, these two vectors, if you look at them like this, one going this way and one going this way, what's going to be the sum of these two vectors? Right up the middle. So this guy will be slightly polar, with this side being slightly positive and this side being slightly negative. So you have to be able to adapt when you're trying to figure out the molecular polarities. Is you want to take a look at both situations, adding up the vectors, or also which side's got the most electronegative atom. Now, as far as adding up the vectors go, I also call it walking the dog. So imagine that you are a person here, and these arrows are connected to dogs that you are walking. And since these are all fluorines, these dogs are all the same size. You have two dogs pulling you left and right, if you will. I'm going to turn this around. You have two dogs pulling you left and right, and then you have these two dogs pulling you up. Which direction are you going to go? Straight up. So when you go straight up, as you can see here, that's going to define your molecular polarity. The direction shows you the slightly negative side. The other side's the slightly positive. All right, so we've assigned molecular polarity here. Now let's take a look at the other one here, NF3. So we've got 5 plus 21, so 3 times 8 or 7 is 21 for 26 electrons. So we're going to put a nitrogen in the middle. We're going to put fluorines here, and we're going to put lone pairs around the fluorines. and then the last two right here. So here we have 4 pair. And let's see what we do next. Okay, so here we have 4 pair. So we're going to make this tetrahedral. I'm going to put the lone pair at the top. I'm going to put the fluorines at the bottom. And remember, for the tetrahedral, we do a wedge and a dash. So it looks like a 3-legged stool. Can you see that the bottom of the stool has the more electronegative atoms? So there's your molecular polarity. So this one is a lot simpler than this one. This one was a little disconcerting because these 2 fluorines that were opposite of one another. But remember, when you have opposites like that, they essentially cancel each other. Since these 2 are not opposites, they reinforce one another. And so that's why the molecular polarity ends up going to the left. Okay, so there we go. And finally, we have this problem here. 1,2-dichloroethylene can exist in 2 forms. Is either of these planar molecules polar? Well, let's first decide if they are indeed planar. Well, actually, we'll leave that to another time. That's actually the next section. So we're going to assume that the author is correct and these are planar, because they don't necessarily have to be planar. For instance, if we take a look at A, couldn't we draw it like this? That's trigonal planar, and that's trigonal planar. So we're going to assume that the author is correct and that this is flat and planar, and this is flat and planar. So here we can do the vector way, or we can just take a look and say, are the more electronegative atoms on one side? Here they are on one side. So I'm going to redraw the molecule and show you how they're both on one side. So here's the slightly negative side, and here's the slightly positive side. So when we go side to side here, this is what we draw for the molecular polarity. Now, we wouldn't want to show the work like this. We'd simply want to show this molecule with an arrow next to it like this, pointing from the slightly positive side to the slightly negative side. Now here, if you take a look at these 2 chlorines, are they on one side? If we draw a line to the 2 chlorines, are they going to be both on one side of the molecule? And the answer is no. They're going to split the molecule in 2 evenly. So this one's going to be nonpolar. So this is how you indicate that a molecule is nonpolar. You use the word nonpolar. Okay, so that's that example. Now I have one more problem here, and it's the following. Use the molecular polarities of H2O and NH3 to show why they mix fairly well. So let's do that. So here's H2O. H2O has 8 electrons. You're going to put oxygen in the middle. So here's your Lewis. Then you're going to say, oh, I've got 4 pair. 4 pair is going to be tetrahedral. So if we draw a tetrahedral, it looks like this. And then when we fill in the blanks, in this case, it makes the most sense to put the lone pairs on the wedge and the dash, and the hydrogens here. Now we can rotate this, and that's fine. So here I've rotated it. And you can see that the more electronegative atom is oxygen, and it is on one side, and the hydrogens are on the other side. So if I split this molecule in 2, you can see the oxygen's on one side, the hydrogen's on the other. So there's the molecular polarity. Now for NH3, it also has 8 electrons. And this one's going to be pyramidal, triangular pyramidal. triangular, pyramidal. So when I draw this, it's going to look like this. Three-legged stool, and again, we're going to draw an arrow going up towards the more electronegative atom. Now, if you really want to draw these arrows correctly, you draw this one as being shorter because nitrogen is not as electronegative as oxygen. So we can think of this molecule here as being like that, slightly negative and slightly positive. That's supposed to be a negative, so I'm going to erase this and make that a negative. Okay, and this molecule here, and I'm going to put a little oxygen here on this side, is going to be the same orientation, slightly negative and slightly positive, and the nitrogen here is at the top. So how will these two molecules mix together? Well, if I have the oxygen here, and this is slightly negative, and this is slightly positive, then that means that we would have the nitrogen here, and this would be slightly negative and slightly positive. So do you see that the opposites are attracting? So these molecules actually mix pretty well because the opposites attract. Okay, now use the molecular polarities of H2O and CH4 to show why they do not mix well. Well, we already have H2O. H2O looks like this, but CH4, without going through all of the steps, looks like this. It's nonpolar. So we're going to let this slightly negative and slightly positive represent water molecules, and we're going to let this represent the CH4 molecules. So here, what's going to happen when you mix these two together is that these guys are going to do something like this. So you're going to have a network of water molecules where the positive is next to the negative, and this just goes on and on and on. And where are these guys? These guys are sad because they're on the outside. They can't get into the middle of this because they don't have any attraction for the other molecules. So these guys, because they're so tightly knit together, so tightly bonded together, so to speak, they exclude the nonpolar molecules. And that's why water and CH4 don't mix very well. You can get them to mix a little bit, but they don't mix very well. Okay, that's it for this section. Thank you for listening.